Okay, class, now let's take a deeper dive into P control, or proportional control. So now we will have the integral and derivative action in the PID controller turned off. So the feedback controller now, and we'll just call this P controller, is characterized by a transfer function, which is the pure gain. It's just the controller gain, Kc. And again, the P controller takes in an error signal, and that's the difference between the set point and the actual measured value of the control variable, and it outputs what the manipulated variable should be in order to bring the control variable to the set point. So what the control law is under this context would be, and I'll call it a P control law, is that the manipulated variable is equal to U bar, the steady state value of the manipulated variable, plus Kc times the error signal, E of t. So it's proportional. The controller action is proportional to the error. And I'll expand this out because I want to emphasize that Kc is the set point minus the measured value of the controlled variable. So there are 2 points for P control. So this here is the controller gain. Okay, this is the controller gain. So this is our controller gain. And the controller gain is the only tunable parameter in P control, right? In addition to U bar, I suppose. So 2 points. We can tune the magnitude of Kc to have a more or aggressive controller. For a more aggressive controller, we make this large. And I use the word aggressive because if Kc is large, and for a small error, there will be a lot of controller action. So that would be an aggressive controller. Not so aggressive controllers if Kc is small, and then the error needs to be quite big in order for the controller to take a lot of action. So besides the magnitude, we also need to choose the sign of Kc appropriately. By sign, I mean whether or not it's plus or minus. And we do this to ensure that the controller acts in the appropriate direction. And we'll have a handout on this. To expand more. But we want to make sure, okay, if the error is negative, how should we change the manipulated variable to adjust y? And that depends on the process in the appropriate direction. Okay, so that's a P controller. Introduce a little bit of nomenclature here. If Kc is greater than 0, then it's called a reverse acting controller. So I suppose this can go down here below here. Okay. And on the other hand, if Kc is less than 0, then it's called a direct acting controller. And it's sort of odd that it's called reverse acting when Kc is positive. But the reasoning behind this is because this is based on the measurement instead of the error. So I'll write that down. This definition is based on the measurement not the error. So to expand on that, let's say ym, the measurement of the control variable, let's say that increases, right? So here's ym. So if this increases, and if Kc is greater than 0, then what happens to the manipulated variable is it decreases. Okay, so the controller output decreases. All right, and so that's why it's called reverse acting, because if the measurement goes up, then the controller output goes down. Direct acting controller, on the other hand, if the measurement goes up, and if Kc is less than 0, what happens is the controller output actually increases. And so that's why it's called direct acting. So that explains this terminology. So let's look at P action. So this would be P action. I should label this P action. So this is ideal P action. And in reality, P action is a little bit different than what we idealize. So in fact, the entire controller output is composed of P action here. So I can put U here. This is U as a function of T. Okay. Oh, sorry. What we should look at is the P action as a function of the error signal, right? E of T. This is E error. Okay. And what P action looks like is this. Okay, so this here is when the error is 0, the controller action is U bar, right? That's the bias. And then the more as the error increases, then the controller output increases as well. And the slope of this line is the Kc, right? Because U equals KCE. Okay, so that's sort of trivial, but I just want to show that as E increases, the controller output will increase. But it depends on the sign of Kc, whether that's negative or positive. But yeah. But in reality, this is an ideal situation, because in reality, for example, control valves, they can only be fully open or fully closed. They can't allow an infinite amount of flow, obviously. So in practice, what it might look like is something like this. So there might be a minimum flow, right? And then there's also a maximum flow, right? So the controller output actually saturates, okay? So again, this is U bar. That's your steady state value when E is 0. And again, the slope of this, and we're assuming Kc is positive here, is Kc. And it turns out that there is a maximum controller output, U max. And there's a minimum controller output as well. And in practice, this can arise in several different settings. So I'll write this down. The control element has limitations. And so for a few examples, if a control valve is fully open or fully closed, there's only a maximum amount of flow it can allow, a minimum amount of flow. Another example is if the electrical power to a heater is maximal, there's electrical power limits. And that would give you a maximum, right? This would give you U min and U max. Another one might be a pump where the fan blade on the pump reaches a maximum angular velocity. So a max pump speed. So you might be able to stop pumping and achieve a 0 flow rate. But there's also a max pump speed, and that would saturate the controller output. So this is something to keep in mind, and in Studio you'll explore this. But obviously, P action is proportional to the size of the integral. Size of the error, sorry. Okay, so this is a meme that characterizes what we'll study next. And so this person is asking, oh, so you're using P control. How did that set point change work out? And the reason this is funny is because P control results in a steady state offset. So if you make a set point change, the control variable will never reach that new set point, even after an infinite amount of time. There's steady state offset. And that's a negative of P control. And later we'll correct that with PI control. But first, let's understand why that's the case. So let's look at the servo response under P control. And so we're not even thinking about a disturbance here. So there's no disturbance transfer function block. So the only input is this. So this is our input set point, and then we're looking at the output here. This is our controlled variable. And then we have a P controller right here. And the P controller outputs a manipulated variable based on the error signal. And then this manipulated variable, in turn, through the process, influences the controlled variable. And let's, for the sake of simplicity, consider a first order process. So we're considering a specific process. And what we derived before is that the servo response, so this is your servo response, closed loop servo response. This is a closed loop transfer function. So we derived before, and you can derive this on your own, again, if you'd like, that the closed loop servo response is GC times GP over 1 plus GC GP, right? And then if we plug in these specific control law, this specific process, what we get is KCK over tau s plus 1 over 1 plus KCK over tau s plus 1, okay? And that's a mess, but if we multiply by 1 in a fancy way, by tau s plus 1 over tau s plus 1, then we get KCK over tau s plus 1 plus KCK. And we'd like to get this in standard gain time constant form. So we want to make that a 1, right? So we can again multiply by 1 in a fancy way. And we can write this in standard gain time constant form as KCK over 1 plus KCK over tau over 1 plus KCK s plus 1. And voila, it's in standard gain time constant form. So this here is the gain. I don't like this thick pen. So this is the gain. And we'll call it K hat. So this is the gain of the servo response. And this here is the time constant of the servo response. And we'll call that tau hat, okay? Okay. And there are two things to note about the servo response. So first of all, it's first order. So P control results in a first order servo response if the process itself is also first order, okay? So that's one thing to note. So first order servo response for P control first order process. The other thing to note is that the response tau hat, the time constant in the response, since you're dividing by a number here, 1 plus KCK, and we'll later argue that KCK has to be positive based on the sign of the gain in a future lecture. This is actually smaller than tau, okay? Because you're dividing it by a number that's greater than 1. And what that implies, so mathematically, what that implies is that the time constant for the servo response is smaller than the time constant of the process. And so the closed loop dynamics are faster than the intrinsic process dynamics. So by outfitting this with a P controller, then we can achieve dynamics that are much faster than the time scale of the process. So closed loop dynamics faster than the intrinsic process dynamics. So that's quite interesting. And the larger you make KC, the more this becomes true. The more extreme this statement is, I should say. Okay. And the other thing to note is that K hat, that's the gain of your servo response, is actually less than 1. Okay, so there's no way that this can be greater than 1. It's less than 1. And that's bad news. So I should actually put a smiley face next to this one. So that's some good news. Okay, and this is bad news. Because what that means is there will be steady state offset, and the B controller will never allow your control variable to reach its new set point. Because think about it, if you make a unit step input in the set point, what you want is eventually y to increase by 1. But what this is saying, y is going to be increasing by a factor less than 1. Because remember, the gain is a scaling factor for the input. So this implies will be steady state offset. So increase set point by 1 implies y star as t goes to infinity, even after an infinite amount of time, will increase by k hat, which is less than 1. So not great. That's bad news. So let's consider a step change in the input based on this servo response here, okay? Okay. So let's say this is your original set point, and then you bump it up by m. Okay, and of course, in deviation form, what that means is your set point, it's initially 0, and then you bump it up by m. Okay, so this is a unit step input. And we remember from CHE 361, the Laplace transform of unit step input is the magnitude of that step divided by s. Okay? And so what we can do is use our servo transfer function here to find the response. So this implies y equals, so it's k hat, it's first order, right? Tau hat s plus 1 m over s, right? Okay, and if you remember from CHE 361, then in the time domain, the response is m k hat 1 minus e to the minus t over tau hat. Okay, so the picture of what this looks like is as follows. So I'll draw one more time. Let's see. So we'll have a shared t-axis here. Okay. Okay. And here we'll have y star set point, and here we'll have y star. Okay, so this is your input. That's a set point change, and this is your output. The control variable under closed loop P control. Okay. And what we've done is we've bumped up the set point by 1, right? Okay. And so this is by m. So this is the set point. This is where we want y star to go. And of course, it's impractical to expect the control variable to go there immediately. And what happens is, okay, here's y. It's at steady state. And then with first order kinetics, it goes to not the set point, but it goes to a value less than the set point, okay? And that's what it looks like. That's the response. And this value here is m k hat. So this is m, right? And this is m here. And this here is m k hat. So it's disappointing. You bump up the set point, and then your P controller does not take your control variable to the set point. They're steady state offset, okay? I'll demark what that is. So this here is offset. And it's steady state offset because it's never eliminated as t goes to infinity. So this is steady state offset. So that is bad news. Very bad news. Okay, so I'll write that down. So there is steady state offset. So we desired y star to increase by m. Instead, as t goes to infinity, y star goes to k hat m, which is less than m. Okay, because k hat is less than 1. We've derived in the previous slide. And so there exists steady state offset error. And let me define what steady state offset error is. So steady state offset error is, and we have to get the sign right here, is what we want y to be, which is m, minus limit t goes to infinity, y star. So this here is what we want y to be. This is important for your quiz. This is what we desire y star to be. And this is what it actually is. Okay? And what this is equal to, in this context, m times 1 minus k hat. Okay? And we can put in what the actual k hat is. So from the previous slide, 1 minus, and then k hat is kck over 1 plus kck. So it depends on your controller gain. And it depends on the process gain, okay? Okay, and this is not 0, okay? We would like the steady state offset error to be 0, of course. Okay, so this is all bad news. For a step change in the set point, y does not reach that set point. There's a steady state offset, and we've derived it as a function of our controller gain. And so an interesting question is, what is the effect of the controller gain, Kc, on the servo response? And the key is to analyze both of these expressions, so k hat and tau hat. So let's remind ourselves. So, well, y star over y set point star equals k hat over tau hat s plus 1, where k hat equals kck over 1 plus kck, and tau hat equals tau over 1 plus kck. Okay? And so now let's plot these. Let's plot k hat, okay, versus kck, okay? So here, this is if your controller gain increases. In magnitude. So this is a more aggressive controller as we go to the right here. Okay, and what we see, use a different color. What we see is if kck is 0, then of course nothing happens because you have no controller, and so you make a set point change and nothing happens. Okay, so you start out here. And then as you jack up your controller gain, what happens is it saturates. And eventually it does go to 1, okay? So the more aggressive your controller is, the higher Kc, the more that k hat will go to 1, and then your steady state offset will go to 0, okay? So as a result, let's also draw what the steady state offset looks like. This is your offset. Offset, and remember we derived what the offset was. It's m times 1 minus k. And this is also a function of kck. Okay? And so again, if you don't have any control of the offset, starts off at m, right? Because you're not doing anything, and y is going to stay as it is at 0, even though you made a set point change of m. But then what will happen is if you increase your controller gain, the offset will eventually decrease to 0, okay? So the more aggressive controller you have, the less offset. So I'll write that down. More aggressive controller applies 1, the offset diminishes. And actually what happens is, I'll show you. So here, so let's say you plot this is your control variable with a more aggressive controller. So it will actually look like this. So we'll go closer to the set point. It never quite gets there, but it goes closer. That's with a more aggressive controller. All right, now let's also look at what tau does. So what also happens is 2, if we look up here, okay, let's look up here. If kck increases, then this tau hat becomes smaller. Tau hat decreases, implies faster response. So it intuitively makes sense, right? If you have a more aggressive controller, you have a faster response because you take more drastic error once you take more drastic control action once you see a given error. Okay? So I think this is a nice analysis. Even though it's a very simple scenario where your process is first order, we can derive, based on our controller gain Kc, what the servo response will look like, right? And what we've found is that there will be steady state offset with key controller, which is bad news. And for your homework, you will do the same analysis except for analyzing the regulator response. So whenever you have a disturbance, and you want to keep the set point at 0 to reject the effect of the disturbance. Sorry, you want to keep y at 0 to reject the effect of the disturbance, but the set point is 0. And so this analysis suggests, well, why wouldn't we always just make Kc extremely large? Because if we increase Kc, then what happens is the offset diminishes and we have a faster response. That's wonderful. And you're right, under this simplistic setting, in this simple model, that is what the math tells us. But in practice, that is very misleading. And so, yeah, why don't we make the controller gain Kc very large? Indeed, based on this analysis, a big magnitude of Kc leads to a faster closed-loop response and smaller steady-state offset. But there's something we're neglecting here. So in practice, there are no processes that are first order without a time delay. And it turns out that there are higher order dynamics that we're neglecting here that are present in real processes, as well as time delays. And if you include these in the math, what you'll find is that aggressive controllers, i.e. controllers with a large controller gain, will destabilize a process and it will result in oscillations. Okay, and often it's better not to have a controller at all than to tune a poorly tuned controller. And so often what will happen, if you have too aggressive of a controller, this is your manipulated variable. So this is your P action or your controller output right here. Okay, so what will happen is, let's say you make a set point change of 1. So your process is at steady state, right? If you have too aggressive a controller, what will happen is your control action will shoot up, and then basically the control valve will fully open, okay? And then what will happen is it will shoot down. Your control valve will remain fully closed, right? And then it will shoot up and remain fully open for a while. and then it'll shoot down. So this is what something it will look like. So what you'll see are bang bang of the control valves as it goes up and down. And you'll see oscillations. And this is a result of an instability. And we can actually show this with the mathematics if we account for higher order dynamics and time delays, which we'll do later. So yeah,